in the room, but not your face, not your...
Okay, guys, we're about to be live. So now we're basically official ones. I'm going to introduce you very briefly and then you go.
Yeah.
Okay, let's see.
The room, but not your...
Perfect, we are live. Okay, cool, we're screen sharing. I think we're good. Yes? Okay, so welcome everybody to our first session of the day, of the first day on AI in the environment. We welcome PySchool, we welcome Francesco, Cristiano, and Sebastian here to the session. I'm just going to spend the first 3 to 5 minutes, not even really 2 minutes, introducing them because I want to give them full space to their workshop and to give them full time to present their research. Okay, so very briefly, what is the workshop going to be about? The title is Leveraging NLP to Achieve Environmental Sustainability. And the description is mapping the environmental capabilities of EU countries to check if they match the need for clean technology as implied by the European Green Deal is becoming crucial. One way to achieve this is to retrieve geolocalized documents describing R&D activities across the EU and the world. Under a contract with the Joint Research Center of the European Union, they carried out a project which is called Patents for IPPC, consisting of building an information retrieval engine capable of fetching relevant patents based on specific subsections of some official documents. Following recent advances in the field of NLP, they built a retrieval system based on the transformer architecture. They will give here an overview on the project and take the opportunity also to explain NLP pipelines and good practices. So the workshop today will be given by Cristiano De Nobili, Francesco Cariaci, and Sébastien Bratière. I here introduce the workshop leader, which is Cristiano De Nobili. He's a theoretical physicist, now lead AI scientist at PySchool, working mainly on environmental impactful projects. He was previously an NLP and deep learning scientist at Samsung's Bixby project. And he describes himself as a science communication enthusiast and civil pilot. Wow. And the other workshop's leader is Francesco Cariaggi. Francesco holds a master's degree in computer science from the University of Pisa in Italy. He currently works as a deep learning engineer at PySchool, where he helps businesses grow with the help of AI. And they are accompanied today by Sébastien Bratière as well. So please, guys, I leave you the floor. Go ahead, and I welcome the audience to share questions in the GatherTown chat, and they will be replied at the end of the workshop. The floor to you guys.
Thank you so much for the introduction. It's a great pleasure to be here today and to be having this first workshop of the day. Really excited about this. So I'm Sébastien. I'm going to tell you a bit about the context at PySchool in which we did this project, so that you understand why we came to do it and what it means for us. My own background is in NLP speech recognition. I did my master's in Cambridge a long while ago and worked in the industry of speech recognition, virtual conversational agents for a while before returning to Cambridge to do a PhD in probabilistic machine learning. I worked on, so that my research was about support vector machines married with Gaussian processes, married with conditional random fields, and a probabilistic model around this. And I worked with the group there with Professor Zubin Garamani. And done with my PhD, I started working with PySchool and PyCampus. So what is all this? PyCampus is an investment fund. And so PySchool is one of the companies that's funded by PyCampus. PyCampus invests in applied AI startups. And we've made 52 investments by now in 5 years. Every time we invest between 50 and 500,000 euros. In exchange, we take a share of the companies we invest in, about 1 to 10%. We invest in companies at seed stage. So this is really early stage. It's companies that are incorporated maybe have a minimum viable product and are starting to demonstrate some traction. So half of our investments are in Italy, and some of them are actually physically co-located with us in Rome, in the startup district that has the same name. It's PyCampus. And so what you see on the right here is a picture of one of the villas that we have turned into offices. And the people at the bottom, I reckon, are from one of our, I recognize a couple, like from one of the startups of PyCampus that was called Wanderio. That was a while ago. Wanderio was selling multimodal transportation tickets, and eventually was acquired by Europcar. The rest of the startups we have are in the world, in Europe, in California, a couple in Seattle as well. And out of the experience with PyCampus, seeing the lack for AI talent, especially in Europe, we decided to found the School of Artificial Intelligence at PySchool. And School of AI is the name of this program we run several times a year, which is hosted by PySchool. It runs several times a year. The next session is due to start on 29th of November, so in like 10 days. It's session number 9. We've every time we're doing projects that are handed over to us by industry, projects that revolve around business problems, but with an AI solution. And what we do is we match the projects up with AI engineers that come and apply to PySchool. So you might be interested in doing that, you guys in the audience, which is why we have the apply to the School of AI link at the bottom here. So if you're interested in this program, come and check it out. It might be a bit short to have you onto the upcoming edition, but if you're really quick, and if we're really quick, but we usually are, then we can make it work too. And the session after that would presumably start in May 2022. How it works is we get these projects from industry. We match them up, as I said, with those participants that we call fellows. And then we have some mentoring and coaching, both internal to PySchool and external, with people. I think here's a couple of the mentors indeed on that slide here. So Łukasz is a researcher from Google Brain. It's one of the inventors actually of the transformer model, one of the authors of the Attention is All You Need seminal paper from 2017. And these are 4 faces: Ricardo, Max, Novi, 4 of our mentors, but there are very many more. And we're advised by, I would say, veterans from AI, Alex, Hassan, Marcello. Alex is a serial entrepreneur and computer science professor at Carnegie Mellon and Karlsruhe Institute of Technology. Hassan is, actually my slide is outdated, is no longer the director of AI at AWS. Used to be that, but now he started his own venture, AI Explain. And Marcello is one of the most cited scientists in machine translation. Used to be head of the human language translation unit, but is now actually a principal scientist at Amazon. Our principles for School of AI: merit first. So we have a selection process here. People who apply go through a process that's very akin to a technical recruitment process. Learn by doing. So the learning experience for whoever participates is based on doing, running into issues, solving them with the help of our mentors. And we work on real world projects, not on simulation. So it's unlike a boot camp. We don't have anything like frontal lectures or stuff. We learn from projects and we try and apply state-of-the-art algorithms. So that by that I mean stuff that's been published within the last 12 months or so. Usually we implement algorithms, like maybe a deep learning algorithm that's been published on arXiv or in a machine learning conference. We adapt it, we customize it to the case that we're working on, and then we hand over a working prototype to our stakeholders. Here are a couple of examples of the challenges that we have carried out. So in this format, we've done 72 challenges so far, and we've trained 150 alumni. So you can see there's a bit of everything from computer vision, natural language processing, data science. I'll just gloss over a couple. one really interesting one for this audience here is we did 2 projects actually with the European Space Agency. We won't speak about them today, but you can go and check them out. There's even the code, the source code we wrote for the ESA projects is open source on our GitHub, so you can check them out. There are 2 really interesting things. One is on crop field image segmentation and classification, and the other one is on the development of a new perceptual loss for a Wasserstein loss for hyperspectral imaging using data from the European Space Agency satellite fleet. Okay, so as I said, next session starts in a couple of days. You're welcome to apply, and I hope to hear from many of you. Now I'd like to leave the floor to Cristiano and Francesco, who are going to tell us about this really exciting project. And you'll see, hearing from them, that a lot of the clever ideas that we tried to put in to solve the challenge that was presented by the JRC are sort of really interesting and sort of generalizable ideas from deep learning applied to NLP. Over to you, Cristiano. Thanks, everyone.
Thank you, Sebastian. Just give me 1 second that I will share my screen.
I'm unsharing now, removing my share.
Here it is. Okay. I hope you can see my screen now.
Yeah, thanks.
Perfect. So, good morning to everybody. I'm Cristiano. As Marta said, I'm a theoretical physicist. I was doing research in theoretical particle physics, but then I switched to artificial intelligence, mainly deep learning, applied to natural language processing, and I really care of all the projects which have impact somehow in social or environmental impact. And now I will talk about the last project I did with Sebastian and Francesco that was in collaboration with the Joint Research Center of the European Union. So we are very proud about this project, and it's about leveraging natural language processing to achieve environmental sustainability. And okay, so I will start with an overview of this collaboration of this project. After that, I will I will smoothly introduce the basics, some basics of natural language processing. Maybe not all of you are experts in the field. And after that part, I will leave the floor to Francesco. So, okay, let's have a larger issue. Let's understand from a high perspective the problem we were faced with. The European Union wants, as you know, achieve net zero pollution by, you see, in the next years, but at the same time, wants to stay globally competitive, of course. And so a fundamental question arises, do the current environmental capabilities of Europe match the need of clean technologies? So it becomes very, very important to map environmental capabilities among countries in the European Union. Recent studies assess the environmental capabilities of countries relying on, you see, international classification or environmentally relevant goods activity as indicators. But this kind of indicators were, let's say, not as precise. They were not as good as needed. So the idea was to think about new strategies. And we worked together with them to find better indicators of environmentally relevant activities. The idea was to use research and development activities as indicator to understand or for assessing the environmental capabilities of each country. So there are these kind of documents that are called BREF, Best Available Techniques Reference, are documents that provide a clear picture of the state of the art about technology and several techniques consolidated and emergent in the field of industrial pollution and control. These documents are compiled by the Joint Research Center and are available there. So our solution to really map this kind of environmental capabilities was to somehow geographically map them, thinking about patents. So you see scientific papers, but mostly patents about the research and development in Europe, considering this kind of documents as a queries to find relevant patents. So you see, at the end of the project, we were able to build an, let's call it, information retrieval system based on transformers. We will talk about them later in a while, that can retrieve research and development relevant patents. But we focus especially to some kind of patents. As I told you before, the industrial pollution sector. That's why the project is named Patents for Industrial Pollution Prevention and Control. So, AI for sustainability. You see, this is a motivational slide, and we want to say you that you see, as AI scientists or engineers, or you see people enthusiasts in AI, we can make a difference to the world. With this project at Pi School, we are doing our bit. So my idea, my personal idea, since I'm not a fan of computers, not at all. So if I have to stand in front of a computer for hours, make sure that there is a strong mission behind, you see, behind the screen. So you see, I sketched the overview of the project. Now let's see some details. So I told you about these documents, BREF, and the idea is, given a BREF passage, find out the most relevant patents. When I say patents, you must think about a technology relative to this kind of patents. So you see, patents are talking about new technologies. And so given a BREF passage, we want to build a model that is able to connect us with the most relevant patents related to that topic. So in order to have a sketch, to have a map of environmental capabilities in Europe, we faced several technical challenges. We are not talking about them in full detail, but just to mention some of them. The project might seem a simple text similarity task, but it's not actually the case. You see, jump from contextual word embedding to sentence embedding for semantic textual similarity. We were faced with linguistic style mismatch between the BREF document and the patents. You see, they are both in English, so this is fine, but they use some different jargon, some different domain-specific language. So we were faced with this kind of linguistic style mismatch. In addition, no training label data were available to us, and the database where retrieve patents was very huge. These were the technical challenges we faced. But now let's start with some basics of natural language processing for non-expert, let's say. So a very cool idea in natural language processing are embeddings, word embeddings, token embeddings. In particular, everything started with non-contextual embedding. So the first step, when you have a sentence or a document, you need to transform each word in a mathematical entity. And the better way, one of the best way to do it is to transform words in vectors. You see, in higher dimensional vectors. So this is the first step for a natural language processing scientist or engineers to be done. After that, we can really think about a model as an engine that is starting from random vectors. You see, for each word, aperitif, spritz, aperol, mozzarella, we start with random vectors in a high dimensional space. But you see, these words may have similar meanings. And so the idea is to build a model, train a language model, means to somehow move this vector in a high dimensional space in order to catch similarities. In this case, a trained language model could be, starting from here, could be to, you see, cluster similar words. So mozzarella stay, unfortunately for it, stays here, but aperol, aperitif, and spritz collect all together because they are similar, okay? So training a language model means starting from random, giving to this model a huge number of documents and somehow understanding similarity and changing vectors in this high dimensional space. So this was the main idea, but unfortunately, or luckily, language is very, very complicated and interesting. And so from non-contextual embedding, we are now trying to understand why people then studied contextual embedding and what does it mean. Think about two different words like spritz and aperitif. They have close meaning, but they are different. In a non-contextual embedding, for each word, we assign one vector. So they can then, you see, become closer. But sometimes a word can have different meaning depending on the context. Let's think about change. Climate change and career change. You see, the word is the same, but the meaning is different. A career change, something positive in this case. But in climate change, the same exactly word could have a negative sentiment, okay? But in a non-contextual language models, we have just one vector to deal with for the word change. So you see, there is an issue. That's why people try to build up contextual embedding. In a contextual embedding, somehow one can have a split of these words in a positive or negative meaning. Now I'm talking about change, so it can have a sentiment, positive sentiment, or negative sentiment. But if you think about another word like second, second has several meanings, more than two. For instance, it could be you can arrive second at a challenge, or you are just arriving at the last second, so second is related to time. So you see, to understand and distinguish different meaning of a word, you need the context. That's why contextual word embedding. And in our project, contextual word embedding were very, very relevant. The state of the art in contextual natural language processing are models based on transformers, such as the famous BERT. You see, we are not now speaking or discussing all the details about BERT, but you need just to know that BERT is composed by several transformer layers And each transformer layer at its core has this kind of mechanism that it's called the self-attention mechanism. This is the really important technology and idea behind the transformers and BERT itself. And the self-attention mechanism helps contextual understanding. So really, self-attention mechanism that was introduced in the paper Attention is All You Need by Google and several others is the real technology and idea, the breakthrough idea for contextual embedding. So another important concept, even from Francesco later will talk about it, is transfer learning. If you need a language model that, for instance, need to know about climate change, you can start not from scratch, but from a pre-trained model that was trained by somebody, for instance, Google, that is aware, knows general English. Then you can train it, especially on climate change text. And so you will end up with a model that, okay, he still knows general English, but somehow it became specialized in climate change words, climate change sentences. And for instance, you see, you can start from a general English model where the word fossil referred to, you see, a historic, prehistoric fossil, but when trained, when fine-tuned, adaptive tuned on climate change text, you see the word fossil somehow get closer to fuels. And so the model starts to have a new idea, a new meaning about fossil, for instance, industrial pollution and fossil fuels. So this is the idea. You start from a general model, knows general English, was already pre-trained by someone else, and you fine-tune on your own problem. So the model, the language model, gains some idea about the topic. So that's what we did. And another challenge was to shift from word embedding to sentence embedding. In case of non-contextual language model, the simpler one I told you before, if you want to switch from word to sentence, somehow there is a simple way. You just need to sum up vectors. Non-contextual embeddings are living in Euclidean vector spaces, so very standard mathematical spaces. You can sum, subtract stuff easily. So this embedding for this sentence, the vector for this sentence could be an average of the word embeddings. For BERT instead, this is not the case. BERT is very useful, but at the same time, it's complicated. The internal geometry of its embedding or of the embedding is going to generate is not actually Euclidean, but something more similar to hyperbolic space. Here, you cannot sum easily vector or use cosine similarity or easy measure to understand the distance between concepts. And so BERT is not a good sentence embedder. It's a word embedder, but it's not a good sentence embedder. For those of you who are interested in the mathematical aspect, the geometry of BERT, I strongly suggest you this link. Then somehow we will share with you the slides so you can interact with all the links that we are showing you. So BERT, the key aspect of this slide is that BERT is not a good sentence embedder. So thanks to SentenceBirth and this other technology, we were able to switch from BERT to SentenceBirth, which is a Siamese network that could be trained in a supervised way, and it's able to generate meaningful sentence embedding. When you have a sentence embedder, then you can compare different sentences for instance, understand that no planet B and save the planet somehow are similar sentences. Instead, no planet B and let's have a spritz are completely different. So we were able to, starting from BERT, and thanks to SentenceBirth and this fantastic paper, to build this Siamese network for our purposes. So thank you so much. If you have any question, just write in the chat, and then we will share with you all these slides. So thank you so much, and welcome to Francesco.
All right, thanks, Cristiano.
Just give me a second. Okay.
Okay, so hopefully now you can see my screen. All right, so now that Cristiano has gone through the kind of methodological aspects of our project, I would like to go a little bit deeper into one of the main building blocks of our retrieval system, which is BERT for Patents by Google. Informally, we could say that BERT for Patents is a good language model, but also not only a good language model, but also a model that is kind of well read in Patent's peculiar linguistic style. But so a question arises, how did Google come up with such a model? Well, you simply start with a BERT model, like Cristiano was mentioning. And by the way, in this slide, the BERT model is represented by the homonymous character from the Muppets show. And after taking this model, you basically train it. We'll see later what it means to train it on a huge amount of patent documents. In the case of Google, they trained it on over 100 million patents. And you do so by a special training procedure whose purpose is to have the model learn meaningful semantic representations of words, and in particular, those that are part of the vocabulary of patents. And so what you get in the end is a model, like I was saying, that is expert somehow in patents language. And what's impressive about this procedure is that it doesn't require any expert knowledge from humans. So let's see how this procedure works in detail. So the procedure itself is actually strikingly simple. The model is provided with short fragments of text, like the one you see here on the screen, where one or more words are masked, so they are covered. And basically, the model is simply asked to predict what the covered words are. And you can imagine that initially the model will guess random words, but eventually it will be able to get there, like in this case. You see that after a successful training procedure, the model will be able to recognize that the word invention or like synonyms like disclosure or application can fit well in that particular space. And so even though this task might seem totally unrelated to what we're trying to achieve, which is to learn meaningful semantic representations of words, it actually is not, because it's actually very relevant, because as you can imagine, in order to be able to predict correctly what a missing word is, you have to deeply understand the surrounding context. And this, in turn, basically forces the model to learn useful representations of the surrounding words, like in this case, you know, all the words present in this text. And once the model is able to learn such representations, it can actually be successful in making the correct prediction. Okay, so let's now see a little demo of how this model works. Now, if possible, I would like you to go to this website here, where an instance of BERT for Patents is hosted, and enter some text in the text box on the right, where you replace some word that you want to mask and you want the model to predict with a special sequence of characters that is as shown here, and then click compute, like in this case. So let's now switch to the web page hosting the BERT model. Let me switch.
Francesco, we can't hear you. I think you're muted. Oh, now we can. Now we can hear you.
Okay, but you cannot see.
No, not anymore.
Okay, let me try again.
Yes,
Okay,
it should work. Perfect.
Okay, so let's imagine that we want the model to make a prediction. And so in this text box here, we insert this text. So I anticipate that the masked model, the masked word in this case is umbrella. And so we'll see if the model is able to actually predict the correct word. So if we click compute, we see that the model is actually pretty confident that the missing word is umbrella, with a probability of over 95%. And this is actually impressive because, as you can see in this short fragment of text, like a canopy is mentioned, a shaft is mentioned, also ribs are mentioned, which of course are not like bones of our body, and the model is actually able to recognize and deeply understand the meaning of these words, and is able to figure out that when talking about the shaft and the canopy, then it's very likely that we're actually talking about an umbrella, and that's exactly the prediction it makes. Okay, so yeah, I've tried with this example, but you can do the same with other texts. Just feel free to grab some short fragment of text from a patent document. For instance, you can go to Google Patents, look for any kind of technology or you can think of, and grab some line of text from the patent, and then mask some word and see the results. So let's switch back to our presentation now. Yeah, so like I said, here are 3 examples that you can use to test the model. On the bottom, you have the example I just tried, and you also have these 2 where the masked words are bicycle and tablet, respectively. All right, so let's see now what were our main contributions to this project. So first of all, we were able to gather several third-party datasets, which is not trivial, like Cristiano was saying earlier, because labeled data for this particular kind of task is not really easy to find. And in particular, we identified 15 different sources of labeled data of the internet. Then we also analyzed multiple evaluation metrics to measure the performances of our trained models. And in particular, we focused on two popular metrics for ranking tasks, which are the Spearman rank correlation and the normalized discounted cumulative gain. We also addressed the linguistic style mismatch problem using fine-tuning ideas. In particular, one approach that we've tried, even though we haven't really finalized it, is basically to have two different models for encoding queries and responses. So contrarily to what Cristiano was mentioning before, when he was talking about a Siamese network. So kind of a network that is composed of two exact copies of the same model to encode both queries and responses. We also tried with two entirely different models to address this problem of linguistic style mismatch. And finally, we also contributed to the expansion of the GS1 or gold standard 1 dataset provided to us by JRC by submitting our model's predictions to human annotators for further refinement. So this table shows the results of our models on 3 different benchmark datasets. And the first 2 rows of this table report the performances of 2 of our best models, whereas the bottom rows refer to baseline models, so the models we were starting from. And as you can see, our models clearly outperform the baseline models, except for the case of the STSB dataset. So the second column, you see that actually the best performing model is this Roberta model here. But there's actually a specific reason for this, because the STSB benchmark dataset is actually intended for generic English. And so since this model here was trained on generic English, it is actually normal that it performs better than our models, which were trained on patents language. And so for patent-specific benchmarks, like these 2 datasets here, you can see that the best performing models are always the first 2. And by the way, these metrics are of the higher is better interpretation. So it means that, well, like I was saying, higher is better. So in conclusion, let's see how the output of our project is being employed currently. So recent feedbacks from the JRC suggest that they are already using our retrieval system. And what's amazing is that they have observed a significant improvement over their legacy systems, and so much so that their expectations were actually exceeded for this particular project. And another good news is that our project has been made publicly available on GitHub under a GNU GPL 3 license. And so this is the link that you can follow to have a look at our repository. For example, here is the landing page of the repository, where you can find all the necessary instructions to like install and try your model to and also reproduce the results that we got with it. So this is the team that worked on the project. There's me, Francesco, there's Cristiano and Sebastian. And we would like to thank you for your attention, as well as the organizers of this conference for giving us the opportunity to share our work. And also, if you're interested, we invite you to apply to the School of AI program offered by PySchool by clicking on the link that you can see here on the slide. The next session starts on November 29th, so it's quite close, but applications are constantly reviewed, and they will be considered also for the upcoming sessions. So feel free to apply and give it a try. Thanks again for your attention.
Thank you so much. Thank you, Francesco. Thank you, Cristiano. Thank you, Sebastian, also at the beginning. The audience could hear you well. They're really happy. They see you from the lecture hall of Gathertown. You are also streamed on YouTube. And now I would ask the audience if they have any questions. We have a couple of minutes left. So do please ask any questions. You will see them appearing here in the Zoom chat. Maybe as we wait for the questions, I have a very general question for you. First of all, thank you. It was very informative, especially for someone like me who doesn't really know much about NLP and BERT. So thank you for that. And in terms of the genealogy of the project itself, I'm curious, how was the idea born? Did you guys from PySchool come up with it and then you propose it to the JRC, or was it the other way around? Just for context, it's for curiosity.
Thanks, Marta, and for the question. And the answer is that, you see, was a mixture of everything. We discussed with them the problem several times, and then we brainstorm a solution, considering also all, you see, the resources we had available at the time. And it's a good news. We can say it now. Sebastian, it's gone, but you see, I can say this news that the European Union founded another project with us, a follow-up project on the same topic. So we are going to advance this model further, and so we signed this week or the week after. I don't remember exactly the day, but so we are going on with this project. So I invite everybody to I shared the slides actually on the chat. There you can find all the links, all the references, also our social account, especially Twitter. We are in the last 6 months we are going to have, you see, updated everything on Twitter and LinkedIn. So if you are curious, you can follow us.
Thank you so much. I let one of the team members share the link to your slides on Gathertown, so everyone has access. Yeah, thank you so much. This makes sense, and congratulations. I mean, this is great news that you're going to continue your project. Really, that's great. Congratulations.
Yeah, thank you so much. And I must say that, you see, AI is applied in several aspects, several fields, but for us, and in particular for me, it's very important to be impactful. This is the role of technology in my case.
Yes, I really loved your quote at the beginning, that as you don't love computer screens,
I hate them.
If you stay in front of them, make it for something that is worth the while.
I hate them, and Francesco knows it very well.
Okay, guys, thank you so much. I think we have no more questions from the audience. In case we have some that occur later on, I'm just going to make sure to send them to you by email. But I'll also see all of you at the roundtable today, right?
Exactly. So see you later, and thank you so much.
See you, and thank you, guys. See you later.
Thank you so much.
And for all the rest of the audience, guys, now I'm going to interrupt the live stream and still stay in the lecture hall where we're going to basically gather to go to the next workshop. Okay, bye everyone.
Goodbye.
Bye-bye.